So gravity is an attractive force between any two masses. So up to this point we've said, oh, I dropped my pen, gravity between the pen and the earth. However, gravity is an attractive force between any two masses. So the pen, not only the pen and the earth, but the pen and me. The pen is actually attracted to me. You and the person sitting next to you are attracted to each other, okay, through the force of gravity. And in fact, you and your calculator are also attracted to each other. And you and anything of mass, there's a force of attraction, okay? And that attractive force we call gravity. All right? So why don't you and your partner fly against each other? Yeah. Good. So because this force is actually a very weak force. This is an extremely weak force. And even though, we can't go about our day without experiencing the force of gravity, in actuality, gravity is actually a very, very weak force. So let's look at what affects gravity. So we're going to look at some dude named Newton. And he came up with what we call the law of gravity, or law of gravitation. And you've probably all heard the myth before, the story of Newton and the apple tree, right? Where Newton was just kind of hanging out under the apple tree, contemplating life, when he actually was looking up at the moon at the same time. And so the idea is he was looking at the moon, the apple falls on his head, and at that moment he kind of had an epiphany where that force of the apple to the earth is the same force between the moon and the earth. And both of those, well, we call gravity, but those forces are equal, and the principles that govern both are the same. And so he kind of derived his equation. He did some more work after that. Derived his equation for gravity. And actually, we could probably conceptualize it together. So, for example, if I have a mass here and a mass here, right? We call this M1, M2. What do you think would happen if one mass was larger? Okay, what do you think would happen to the force between the two? It would increase. Yeah, it would increase. And so as the mass increases, what if we made the other one larger also? What would happen? It would also increase as well. So as the masses go up, what happens to the force of attraction? It also goes up. So this is what we call a direct relationship, and it's dependent on both masses, M1 and M2. So if the mass of one doubled, the force of gravity would double. If the mass of the second one doubled, it would also double again. All right, so that's one factor, and that's the major reason why, okay, my pen falls to the earth, but it doesn't fall to me. Because my pen is more attracted to the earth than it is to me. Why? Because the earth is much more massive than me, right? If I was as massive as the earth, the pen would be just as attracted to me. Okay, what's another factor, do you think? Distance. Good, the distance. So, for example, let's take M1. What if we bring M2 closer? Do you think the force between the two would be stronger or weaker? Stronger, yeah. So the closer the objects get to each other, the stronger the force will be. Now, what kind of relationship is this? Think of it this way. If this is like D1 and this is D2, as D gets smaller, what happens to the force? It increases, yeah. So this is an inverse relationship. As D gets smaller, F gets larger. Mathematically, we put that in the denominator. And actually, we're going to use the variable R instead of D. So let's just define these. So M would be the mass of each. And then instead of D, we're going to use R. And R will become clearer a little bit later, and then also tomorrow for sure. So this is going to be the distance. Now this part is important. It's the distance between the centers of mass. Now we're going to go into a lot more details about center of mass in a future unit, but it's a pretty easy concept. If I have a circle, where's the center of mass going to be? In the center, yeah, in the exact center of it would be the center of mass. So in other words, when we measure distances, we're going to measure between the centers of the two masses and not the edges. Like you wouldn't measure between here and here. You would measure between the center to the center. Okay, we're going to be using meters here. Now, as it turns out, this equation is not so simple. Okay, it's not just mm over r. It's actually proportional to the radius squared, or the distance squared. Okay, which means, for example, if this gets closer, let's say this is distance d, and this is 1/2 of d. The force would go up. How much would it go up? If we cut the distance in half, how much stronger would the force be? 4 times stronger. Yeah, so if this was cut in half, because of the squared factor, the force would go up by a factor of 4. So what's the dominating factor, mass or distance? Distance, yeah. Distance is a much stronger factor. I mean, if we cut this by a third, what would happen to the force? 9 times stronger, right? It'd be 9 times, not just 3 times stronger, but 9 times stronger. All right, there's one more factor here. This is what we call the proportionality constant. This is big G. Big G is referred to as the gravitation constant. Okay, this is just a number. It's just a constant of nature. Okay, that number is 6.67 times 10 to the negative 11. Okay, and one of the purposes of this is really to get the units to work out. Remember, units are just man-made creations, so we're not necessarily going to end up with the right answer, the right unit that we have. So let's figure out what the units would be for this. Notice if you have mass times mass would give you a kilograms squared. Distance times distance would give you a meter squared. And what do we want to be left with? What's the units for force? We want to be left with the newtons, right? So to do that, we'll simply multiply by a Newton meter squared over kilogram squared. Okay? And when you do that, when you multiply by that, notice these cancel, this cancels, and you're left with newtons. So this is the proportionality. This is how we're going to get to our actual value for the force. Alright, so let's just do a real simple problem. Let's find the force of attraction between you and your calculator.